Hi, I'm Professor Goins, and welcome to the Math Professor's YouTube channel. If you find the content to be useful or interesting, please consider giving us a subscribe. Also, it would be helpful if you would like our videos, comment on our videos, share our videos. Any interaction would be greatly appreciated because it would then help us grow. In this video, I'm going to take a look at the integral of a power series. We'll look at both definite and indefinite integrals for power series. First and foremost, as a reminder, a power series is a function of the following form. It is an infinite series, but it's a special type of an infinite series where we have two components. I've got a constant, this coefficient could be come from a sequence, so each coefficient could be different along the way. And then I've got x minus a to the n, so I've got integer powers of x minus a. So again, Cn is a real sequence and a is a fixed real number. Here's a specific example of a power series. Sum n equals 0 to infinity of 2 to the n, x minus 1 to the n. Again, if I were to expand this out using a summation, here's the first, let's say 1, 2, 3, 4 terms. We can see that we get each coefficient comes from the sequence, the 2 to the n, and then we've got factors of powers of x minus 1. Again, if I were to multiply these out, this would be sort of an infinite polynomial, right? A polynomial sort of object with infinitely many terms. Now what I can do is let's take the antiderivative of this. So let's take the indefinite integral of it. Antiderivative of 1, of course, would be x. Antiderivative of 2x minus 1, 2x minus 1 squared over 2, and so on and so forth. So we can take the antiderivative of each one of those individual terms, and again, this is going to generate another infinite series. If I take all these terms here and I find the general pattern, we can incorporate that back into summation notation. So then writing as a series, just kind of summarizing what we found. If I take the antiderivative of this, which of course would be the antiderivative of this, said differently, the indefinite integral, we come up with this following infinite series. Well, let's look at the pattern. We have, first and foremost, I've got a fraction bar in there. I have a power of 2, so each one of those in the numerator has a power of 2, so let's put a 2 there. I've got factors of x minus 1. And then each one of those has that in common. And then what's changing? Well, let's start with the denominator. I've got, so going backwards here, I've got 4, 3, 2, 1, or 1, 2, 3, 4, and then of course the next one would be 5, 6, 7. Therefore, we can say that the denominator is going to be, let's say, n. Just think about that for 1 second here. Okay, and then the exponent on 2. Well, it matches the denominator, so it's 1 less than the denominator. So this is 1, this is 2, this is 2, this is 3. So therefore, this would be, actually, let's do it this way. Let's say that the exponent on x is n. So that would be, this would be 2 to the first, 2 to the second, so this would be 2 to the 0. So let's make this n. Then the denominator would be 1 more, so that would be n plus 1. And then notice the exponent matches the denominator, so that would make that n plus 1. We can do it either way. There's nothing wrong with the way that I originally did it, but I wanted to eliminate a shift of index here. And then notice that the initial term here would start with n equal to 0, so we get the sum n equal to 0. If I would have kept it the way I had it, which would have been fine, this would have been n, this would have been n minus 1, this would have been n minus 1, and then we would have just had to do a shift of index to get it back to 0. So just saved a step. Well, let's summarize what we have. If I take the indefinite integral of this power series, well, if I just ignore the summation and just think of this as one term, 2 to the n's a constant, and add 1 to the exponent, divide by the increased exponent, so that'd be n plus 1 over n plus 1, or n plus 1 to power, and then divided by the increased exponent. So all I do is integrate term by term. Okay. So again, it's a pretty simple calculation. It just looks a little complicated notationally because I've got integrals and infinite series and things like that. But it's at the end of the day, it's a pretty basic concept. what I want to do is I want to look at a few examples of computing antiderivatives of infinite series. First example. Consider the following. Let's compute the indefinite integral of the following. The sum n equals 0 to infinity of x to the n over n factorial. Well, what this says is in order to compute this integral is I can just compute the integral of each term. Said differently, I can actually interchange the integration and the summation operation, meaning this would be the sum n equals 0 to infinity of the integral of x to the n over n factorial and then dx. So in other words, we can interchange summation and limits on its interval of convergence, but that's another story. Okay, so then this would be the sum from n equals 0 to infinity. Now, antiderivative x to the n, again, n factorial is just a constant, so let's just bring that out front, 1 over n factorial, and then the antiderivative x to the n would be x to the n plus 1 over n plus 1, which would be the sum n equals 0 to infinity of x to the n plus 1 over, and then n factorial times n plus 1 would be n plus 1 factorial. So again, I just take the antiderivative of each term. Okay. Next example. Let's look at the following function, the sum n equals 0 to infinity of x to the n. Now remember, this is a geometric series which converges only if the absolute value of x is less than 1. And I also know that this is equal to 1 over 1 minus x. Okay. All right, so let me clean up over here. Just make sure that's dry enough. Okay, that should be good. Okay, so let's compute the antiderivative of that. The integral of the sum n equals 0 to infinity of x to the n dx. Once again, is I just take the antiderivative of each term. Therefore, this would be the sum n equals 0 to infinity of x to the n plus 1 over n plus 1. Okay. Now, what we can do using this geometric series is we can compute some integrals of some very complicated functions. In other words, some functions that no other integration technique would allow us to compute. For example, suppose I wanted to evaluate the following. Let's keep it as an indefinite integral for the moment. Let's do an integral of 1 over 1 plus x to the fourth. Well, if I match this expression, the integrand, up with what I have in this box, let's look at the following. I can write this as 1 over 1 minus negative x to the fourth dx. And then negative x to the fourth plays the role of this term right here, meaning this would be the same thing as the integral of the summation of negative x to the fourth to the n, because notice that this term here again plays the role of this term, and that's going to be what's underneath your power of n. Well, let's clean that up a little bit. This would be integral summation negative 1 to the n. So it's going to be an alternating series, and then x to the 4n. And then this just turns out to be an infinite series. Negative 1 to the n, x to the 4n plus 1 over 4n plus 1, and then of course plus a constant, which I guess I should have put that over here as well, since this is an indefinite integral. Okay, so here's the trade-off. Think prior to power series. Think back in your integration technique chapter. This, well, yeah, no, there's not really any integration techniques that would have allowed us to compute this. So what we do, if I turn this into a power series, we can actually integrate it really, really easily. And you're like, okay, that's great. The problem is, if this turned out to be a definite integral, then that means we'd have to evaluate this infinite series. Let's say this goes from 0 to 1. Then, of course, if I plug 0 into this, that's all 0, so that's cool. But then if I plug 1 into this, I've got this alternating series, minus 1 to the n over 4n plus 1. And in order to evaluate that, well, by hand, all we could really do is we could just approximate it. Say, take the first 10 terms or something like that, and give a pretty good approximation to the value of this integral. But again, I'd have to compute an infinite series, so hopefully that the antiderivative is in some form where actually I could actually compute the value of it. But generally speaking, it'd probably just end up being an infinite series that we'd have to approximate. I want to take a look at one definite example where we can actually find the exact value of it. We don't have to just approximate it, we can actually find the exact value. So let me go ahead and run through this next example. And let me clean up the whole board, actually. Along the same lines of the previous example, what I want to do is let's compute the following. Let's look at the integral from 0 to 1 of 1 over 1 plus x squared dx. Okay. So, solution. What I'm going to do is I'm going to think of that expression as it's the value or the expression resulting from a geometric series. In other words, I want to start by writing this as 1 over 1 minus negative x squared. So that means this would be the integral of the summation of negative x squared to the n. It's very similar to the previous example. 0 to 1. And then this would be integral 0 to 1 of the summation of -1 to the n, x to the 2n. Okay. And then compute the antiderivative of this, which is just the power rule on this one, and then evaluate from 0 to 1, meaning this would be the summation n equals 0 to infinity of -1 to the n, x to the 2n plus 1, divided by 2n plus 1, evaluated from x equals 0 to 1. Plug in 1 to n for x, that would give me the summation of -1 to the n, and then 1 to the 2n plus 1, so 1 over 2n plus 1. And then minus, when I plug in 0 for x, every term is going to be 0, so the summation of zeros is 0. And therefore, the value of this definite integral is given by this infinite series. Now, what I could do is say, okay, well, let's approximate that. Let's plug in a variety of terms. If I plug in n equal to 0, I'm going to get -1 to the 0, which is 1. 1 over 2 times 0 plus 1 would be 1, so I get 1. Plug in 1, I'm going to get minus 1 over 2 times 1 plus 1, which would be 3. And then notice it's going to be alternating, and every denominator is going to be odd. Therefore, I get 1 minus a third, plus a fifth, minus a seventh, plus a ninth, etc. Now, of course, poor planning on my part. I did not grab a calculator. But if you compute those, you're going to get approximately 0. Depending on how many terms you take a calculator yourself, but you should get approximately 0.7. And then again, the rest of the decimals is just going to depend. I don't remember what it's like 70, I think, but we'll hold off on that. 0.7 for sure, if I take at least those terms there. All right, so then you say, all right, well, that's great. I was able to approximate it, but it'd be nice to know the exact value. Well, remember, we actually know what this is. The antiderivative of 1 over 1 plus x squared comes up fairly frequently. So let's do solution 2. We know that the integral from 0 to 1 of 1 over 1 plus x squared dx is the inverse tangent, and then 0 to 1, which would be tan inverse of 1 minus tan inverse of 0. Tan inverse of 1 is pi over 4. Tan inverse of 0 is 0, and therefore the value of the infinite series is actually pi over 4. Well, if computing it this way, I get pi over 4, and computing it this way, I get this infinite series. That means that pi over 4 is given by this infinite series, or the infinite series gives the exact value of pi over 4. And therefore I get the following result. I know that the sum from n equals 0 to infinity, this alternating series of odd denominators, gives exactly pi over 4. Now if I want to, say, solve this for pi, we get this result right here. So this would give you a very, very easy way to approximate pi, say with a calculator. Just start adding up terms, and you'll see that the more terms you add, you get closer to the exact value of pi. Okay, thank you for watching.